Okay, we just saw a simple demo of gradient descent. Um, this program essentially, and we saw that it converged to the optimum relatively quickly in a few hundred steps perhaps, depending on the accuracy to which we would like the gradient to go to zero. Um, Now let's actually see what the behavior looks like if we change alpha. Okay, so let's do that. I had commented out some plots here before. Let me just put a small pause. Okay, so let's just run this thing again. So this was what was happening. So the function value was decreasing with iteration on gradient descent. So let's just do it for about 50 steps. Okay, at the end of 50 steps, we have the function value. Well, we can check what the function value is. 0.207. Okay, not quite 0, 0.207. Okay, so it's not gotten too close to the minimum, pretty reasonably close. Okay, now let's see what happens when we increase the learning rate alpha. So by the way, when a program is running or looping through something, it's really a bad idea to plot something in progress if you want the program to run very fast, because the plotting just takes a lot of time. But if you want to visualize something as the thing is running, I guess that's fine if you don't care about speed. Okay, so now we can check what the final result is. I suppose my computer is misbehaving a little bit. So now the y value, which is the function value, is 1/10,000th or 2/10,000th, as opposed to 0.207. So increasing the learning rate certainly has improved the convergence of the optimization. So let's try a little bit more, maybe 0.04. Okay, let me stop this. I think it's probably running slow because my computer is doing other things perhaps, like storing this video. Um, okay, um, let me actually comment these things out and just run that cell. So that went fast because I commented out the plotting. But let's look at what the function value is at the end. It's 10 power minus 10, right? So increasing the learning rate for a given number of steps has dramatically improved the sort of speed with which gradient descent converges, I guess, or converges to the minimum. So alpha learning rate certainly does improve learning rate, as you can imagine. Let's just see what happens if you increase it much more. Let me run that cell, Okay, now you notice that f value, the function value, is instead of being very, very close to 0, has gone actually to 10 to the 15. Okay, so that's really bad. So let's actually see what that looks like. Let me just run 5 or 6 iterates rather than 50 iterations because my computer for some reason is a bit slow. Okay, notice that the function values sort of start decreasing and then start increasing pretty soon. So let me maybe run it for 10 steps, or let's say 10 steps, yeah. And then let me just put this pause here. And maybe we don't really care about the plots. We can just output the function value. Let's just do that instead of plotting it. Oh, there's a pause here. And we notice that the function value becomes higher, 10 to the 4. Yeah, so it sort of keeps increasing, right? Why is that? So the basic idea is that the learning rate, if it is small enough, then you are guaranteed that the function will keep decreasing. Okay, because what is the learning rate? Learning rate decides how far you want to step along the local gradient. The local gradient essentially tells you, or the negative of the local gradient. If you go down along the negative of the local gradient, you will necessarily decrease the function value if the gradient is accurate, right? So it says there's a downslope here. So if you step along it, if you take a small enough step, you will necessarily decrease the function value because that's what the gradient tells you. But of course, if you take too large a step, the function may decrease, but then if you take too large a step, it may eventually start increasing again, right? So that's the danger of taking too large a step. For small enough steps, the gradient gives you a very good idea of how much the function will decrease because the linear approximation is pretty good for small enough steps because the gradient is essentially a linear approximation. But if you take a large enough step, the function may start increasing again, and that causes problems. Okay, so here's sort of the takeaway. If alpha, the step size or the learning rate, is small enough, you will at least make a small amount of progress and you will keep making progress. If you increase alpha a bit or a bit more, you will increase the learning rate pretty substantially potentially. But then eventually there will be a point where increasing alpha any further will make the algorithm unstable. In sort of a dynamic sense, it will make the algorithm unstable and may result in divergent behavior. So You can sort of see that in this kind of a cartoon, which I illustrated in words just a minute ago. So if you have a function of p, taking small steps will sort of go down the function slowly. Taking large steps will go down the function faster. But taking too large a step will essentially, if you start here, instead of going down, you might go to the other side of this bump and then sort of keep bouncing away. So that's kind of the mechanism for this divergent behavior in the presence of too large an alpha. Okay.